number 4. Yes.
Number 4?
Number 4.
Oh. All right. So I'm going to start with the full form. It is steady state. Potential energy effects can be ignored, I guess. So at the inlet, there is a speed we have to take into account. We're ignoring potential energy effects. At the exit, we're ignoring potential energy and kinetic energy. It's insulated. And diffusers are always rigid, so okay, so what we got is I guess m dot times HE minus HI is equal to, oh, well, everything's m dot, so we can divide everything by m dot, and you get this is equal to VI squared over 2. And this is, we're given a speed. We're going to have to convert all this stuff to SI units.
Yeah, I have them here.
Okay. What's the speed in meters per second?
365.76. Pressure one is 6.89 bar.
Say that again.
The pressure at the inlet is 6.89 bar.
Okay.
And then at the exit, it's 20.68 bar.
Okay. And so 365.76 squared over 2. This is 2162.19.
Should be 66,886.
What? You got something different for?
Yeah.
365. Yeah. So
66,890.
Yep, that's what I got. Okay. And oh, it's a saturated vapor at the inlet. That's good to know. Okay, so we can right away look up the, since we have the pressure, that's enough to tell us, we can look up the inlet enthalpy, and then we can just calculate the exit enthalpy. So let's see what we have for tables. Did you look that up already?
61.57.
Okay. So 261.57 0.57, but that's probably in kilowatts, right? Or in
Okay.
kilojoules. So this is times 10 to the third.
Okay, that makes sense.
And so HE then is 328,460. Um, okay, so now we're going to a pressure of 20.68 bar. So we're looking for a pressure of 20.68 bar and a specific enthalpy of 328, 0.5 kilojoules per kilogram. And it asks for the temperature, is that right?
Yes.
Um, so it's a saturated vapor. We are
At the inlet though, so then at the exit would not be saturated.
right. So the pressure went
Oh,
up. So it's probably, it's going to be either a saturated mix, probably, um, or a compressed liquid. But I guess you can always look in one table. If it isn't in the range in that table, then you know it's in the different phase. Okay. So let's try first. So let's see what it is at saturation. So we're looking for so this is indexed by temperature. Okay, here's pressure. So we want about 20 bar, and the range of specific enthalpies at 20 bar is going to be between the saturated liquid and the saturated vapor. So the possible range for saturation is between 150 and 278. We're above that, right?
mm-hmm.
Yes. The one we're looking for is 328. Everyone with me on that? And so let's go to the superheated vapor. I thought it was going to be a saturated liquid or a compressed liquid, but it looks like it's going to be a superheated vapor.
Does the pressure went up so much?
The pressure going up would make it more likely to be a vapor. No, the pressure going up would make it more likely to be a liquid. That's why I thought it was going to be a liquid. But I guess, yeah, the temperature is just going to go up more than that and make up for it. So let's go to 20 bar. That's a shame.
We can interpolate up, right?
Well, that's extrapolating, and we do not want to do that. Well, you can Google it. There are other tables available in other places. Let's see if this is any better, but I think this is probably just what I took those from.
Here, one doesn't go up to the 2 megapascals, so that's closest to close to like 1.6.
Okay. Is this the same table? I don't even.
The superheated one.
Okay.
Goes up to 1.6 megapascals.
Okay. A13. Okay, so we're at a pressure of 20 bar, which is, oh, it doesn't quite make it, 2 megapascals. That's not what I want. Should we just buy some and measure it?
That'd be fun.
Yeah.
Temperature table. This is saturated. We don't want that.
Same thing when not it's carrier.
That doesn't have specific enthalpy. Yeah, I know you.
What makes me feel better for the wall here?
Yeah. So the problem is that our tables don't go up to that range. That's saturated, superheated.
Okay.
So we're looking for 200 kilopascals, right? So isn't that?
Or would it be 2,000 kilopascals?
Oh, 2,000. Okay, and we're looking for a specific 328. So it's somewhere between 100 and 110 degrees Celsius.
So 100, 110, so 3, 22.3, 100.
Yeah.
This is the 2 factor like 4.
Yeah, but we're close enough to 20 bar with our pressure that I would just use this table instead of doing the full.
104.8.
But you could do the 3-step interpolation, I guess, to get a more exact temperature. Yeah, just do the 1-step one on problems like that. If it's close, it sort of looks like maybe it was meant for us to be right at 20 bar. Yeah.
Works for me.
Okay. Well, ooh, that's the last one. Just made it.
So we wouldn't have had anything to interpolate with anyway.
Right, exactly. Anybody want me to talk more about that one? So it definitely would have been ideal if the tables I gave you went up to those values. I cannot argue about that, but you usually can find tables with different ranges online. So
you just said, well, clearly the pressure is too much and the
Yeah, I mean, so listen, like you're doing these daily problems to get ready for tests and stuff, you know. So if that happens, really, I think the most useful thing you could do for yourself is just look at this table, say that it doesn't go to 20 bar, it only goes to 1.6. So just think like, okay, I'm going to say that we calculated 1.6 and then finish the problem that way, you know, that kind of thing. Just know what the steps would be. That's really what you're trying to ingrain is the steps that you would have to follow to do a problem like that. Yeah, ideally you wouldn't have to think about it that way, but I think that's the most useful way to approach that. Any other homework questions you want me to go over?
Mine was weekly assignment number 3. That's stuff.
Okay.
I think I got all the right information from the tables. I'm just not sure what to do with it.
Okay, so it's a saturated liquid. Then you add heat.
Yeah, is this about finding little u at each point?
About the minimum in the vapor.
Yeah, and then just taking it, like multiplying it by the,
Well, it
by
doesn't
the
give us
mass.
quality, so what if we do?
Yeah. Okay, so um, so you know that you have a saturated liquid at 4 bar. So the starting pressure and the pressure is kept constant. So the starting and ending pressures are both 4 bar. And so at 4 bar, you can, you know, this is at saturation. So you can figure out, you know, the temperature. At both of these two cases, right? And you know this is true. So yes, what you were saying is exactly right. So you can look up the specific volume at both of those two cases, you know, and
You mean specific internal energy?
well, maybe we'll have to get to that later, but we can look up, so we know, so don't look this up. Start out by looking up V1 and V2, okay? And that can take you to the volumes. Okay, and now you have a constant pressure and you can just calculate that work. Okay, then once you have the work, then you can go to the first law.
And then you would need to do what I said to figure out what Q was.
So yeah, then I guess you can look up the specific internal energies, calculate the change in internal energy.
And then do some
And then-
algebra to figure out.
Yeah, right, from the first law.
Okay.
Yeah, that's right. Any other questions about that? Like, obviously, I don't want to go through the steps of that, but
Could you give 4 the same treatment? Just kind of talk about the process.
yeah, I think I could do that. Okay, so almost for sure when you get these polytropic processes, you're going to be calculating the work with that integral. Like that's the main thing it's useful for, is coming up with pressure as a function of volume. So no heat transfer. You're given 2 properties at both of these 2 states. So, so first, let's see, are you given? Yeah, you're given enough information that you can calculate A and B. Okay, so you can come up with pressure as a function of volume and calculate the work.
Oh, so you just set like put those 2 equations, and then you have 2 equations or 2 variables.
Right.
For A and B.
Yes. And then that'll let you calculate that integral so you can calculate the work. And then go to the first law. You have the work. The internal energy now, you should be able to, it's just a gas. So you don't have, there's no tables you can use here. You don't know what this gas is. Oh, well, there's no heat transfer. So Q goes away. So you can calculate from getting that integral the change in internal energy. Once you calculate that, then you have the mass. You have the mass. Okay. So part B is easy.
Thank you.
Yeah, sure. Any other questions?
So in the end, once we calculate the integral, you will be negative, right?
Let me see. So it starts, you can just look at the specific volumes. The specific volume goes down, so W should be negative. That's right. So last time I finished talking about.
I believe he did have another question.
Oh, yeah.
It's question 4 for conservation of mass.
Mm-hmm.
Part 1.
Conservation of mass.
Oh, yeah.
Okay. So we have a cylinder. The area here is 1 meter squared. and it's being drained, and the velocity of the water exiting is 2gz square root. Okay, it initially contains this much water. We know the density, so we can figure out the starting height. We can figure out the ending height and do all of this in terms of heights. Okay, so at the start, we know that we have 2,500. That's equal to the volume times the density, which is the area times the starting height times 1,000. So H1 is 2.5 meters. And at the end, we have 900. So H2 is 0.9 meters. All right, and now I think we can just set this up. We know that dm dt in the control volume is equal to the rate that mass is coming in minus the rate that mass is leaving. I don't think it says anything about anything coming in, right? It's just leaving. And so dm dt for the control volume is equal to 2gz square root. And we can write the mass in the control volume as, using this formula, we can write that as 1,000 Z. So this equation becomes the time derivative of 1,000 Z is equal to the square root of 2gz. So that says the time derivative of this is 1,000 dz dt. You with me on that derivative? And that's equal to 2gz square root. And so now finally we can say, so now I'm going to separate variables. I'm going to get all the z stuff over with the dz, and I'm going to get the dt over by itself. So this says, all right, this is 1,000 times 2gz to the negative 1/2 is equal to dt. Right, I forgot the dz over here. And now you can integrate these two parts. So we have 1,000 times the integral from state 1 to state 2 of 2gz to the negative 1/2 dz is equal to the integral from state 1 to state 2 dt. We're just trying to figure out how much time goes by, is that right? So I'm going to rewrite this as, well, we know the starting and ending heights here, so this is from 2.5 to 0.9. And this is for all of these. That was just an algebra mistake there. So 2gz to the negative 1/2 dz. And this, we can say that time at state 1 is 0, and we're going up to t. So this is just going to give us the elapsed time. And so now we have to compute this integral, so you can think of like 1,000 times the integral from 2.5 to 0.9 of 2gz to the negative 1/2 dz is equal to, the elapsed time, whatever, delta t. So this is just all the task is now, is integrating that. So how would you do that? Well, what? I think,
I mean, it's a definite integral, so I think most calculators can do it. I know mine can.
Yeah.
So once it's a definite.
yeah, I guess that's true. You have, right, you can just separate that into a constant. Yeah. I was going to define a new variable and stuff. That's a better way to do it. Just, so it's 2g to the negative 1/2 times z to the negative 1/2, and then it's an easy integral. Yeah. Okay. Who wants to talk about any of these steps? Anybody confused on any of these steps?
So you said that like the ME dot was just square root of 2g over z. I think when I first did, I did something different. It got close, but I got like 0.3 square root 2gz, because I think I did like m dot is equal to the area times the velocity over the specific volume to get it.
That's the velocity of the frickin' water. You are right.
Okay.
This is the velocity of the water. So you have to go.
I did area.
Yes.
Velocity over
So.
And then I got 0.3 square root 2g.
Right. So this really should be.
Volume. Yeah.
Should be the area. Well, that's 1, so that's good. Divided by the specific volume. So this should be 0.001. And so it doesn't change very much, but there's a constant in there that I left out. That's what you got, right?
I think I ended up being like the density times the area of the exit times the velocity. I got 0.3 square root 2gz.
Oh, does it give the... Right, I did the wrong area.
That was a toughie.
Yeah, that's a tough one. So this... Well... So this is equal to negative area times speed divided by specific volume. And that area is 3 times 10 to the minus 4. That speed is 2gz to the 1/2. And the specific volume is 0.001. And so that says 3 e to the minus 1 times 2g to the 1/2. I mean, that you can just calculate times z to the 1/2. So that's about 1.33 z to the 1/2. And I lost a -2, it looks like.
So then your MCV would not be thousands, or would it still? Oh yeah.
This one was right. That was just calculating the mass in terms of z.
Yep.
But this one had 2 mistakes in it. And so now, so let me go through these steps again.
So I mean, this is basically just a calculus question, but when you went from DDT 1000Z, I mean, can you just think of that as pulling the Z into
Yes.
into the differential? You know what I mean?
Oh, as pulling it
You're
into,
taking the time derivative
Yeah.
of 1000Z.
right. So, I mean, I guess it's just, the derivative of, you can pull the constant out. I mean, that's how I thought of it. And then you're just taking the derivative of z with respect to t.
Sure.
So now I'm going to rearrange this as, so 1000 z to the -1/2 dz is equal to -1.33 dt. And now I'm going to integrate both of these. Or I could divide what's 1000 divided by -1.33.
1333.
Negative, no, it goes, well, I'm doing it the other direction. So it's -751.88 times the integral from 2.5 to 0.9 of z to the -1/2 dz is equal to, this is just delta t. And so that should do it.
I went so much deeper into the calculus.
Oh.
I had so many
Uh-huh.
differentials.
First time I did that, I completely messed up the integrals. I was still trying
Yeah.
to do it based off the math.
The first time I did it too.
Cool.
But I feel better about this.
And that's class.
Okay, well, we had some laughs. We had shed some tears.